Hello, my name is Stas Kołszański and I am a senior software developer at MINRES Technologies. In this demo session, we will build up a Python top level for a small VP system. The system is based on the TGC processor and a minimal set of peripherals. TGC is MINRES implementation of 32 bits RISC-V core. So this ISS is representing a real silicon-proven RTL IP. Around this ISS model, we will build up a VP top level in Python and execute a simple hello world firmware. To assemble the test design, besides ISS, we will also use a AON module, core local interrupt controller, router, some memories, and a UART terminal to print messages from the firmware. As usual, we don't want to write the common peripherals from scratch, so we will take a generic router and memories from SCC library. SCC is an open source, lightweight productivity library for SystemC and TLM2. Okay, now let's build a VP top level. In this tutorial, we'll take all the necessary components from the TGC VP repository on GitHub. This is an open source project and you can easily reproduce all the steps done in this demo session in prepared Gitbot workspace. Gitbot is a web-based development environment where we can edit, build and execute code. So all you need to reproduce and play with this demo design is basically a web browser and a GitHub account. First of all, let's prepare the environment. Let's update the wheel to ensure we are working with the latest version. In the next step, we have to download and install PySysC. The installation is a little bit tricky. For the PySysC installation, the location of SystemC library must be known. So we have to set SystemC home environment variable. In this environment, SystemC has been installed with shownn. So we can look up SystemC location in shownn build info file. PySysC needs also to know which C++ standard are we using. So the environment variable stdcxx has to match the C++ version of the SystemC build. In this tutorial we use SystemC library built with C++ 11, so the environment variable must be set to 11. As already mentioned, we are going to use some generic modules from the SCC productivity library. SCC has a Python module for better integration and easier use in PySysC. So let's install it as well. Okay, so that's it for environment preparation. Now we can start implementing the VP top level. We need to import OS path to find C++ headers and libraries. We also need to import logging, for logging obviously. We import cppyy module and we import global from cppyy as cpp, and in this way it will be obvious when we use cpp interface directly in Python. Now we import PySysC and PySysC SCC. From PySysC structural we'll need module and simulation. Okay, let's set the logging level for the simulation to debug. So now we can load all shared libraries that we are going to use in the simulation. In the first step, let's find out where we are right now. We will use the current location to build the path to the location of the libraries. In this example project, some libraries come from shownn. As you might know, shownn is a C++ package manager. So now we call read config from shownn function with the path to the build directory containing the conan file. Then PySysC load SystemC function is called. This function loads not only SystemC but also further Accellera libraries like SCV and CCI. Now we load the shared objects of the SystemC components productivity library. Now design-specific components will be loaded. We start with the instruction set simulator lib, but other libs will be loaded exactly in the same way. For each library, we have to define the include path, and then we load a header file and according shared object file. The huge advantage of the PySysC approach is that any binary library can be directly integrated. It doesn't require any customization. For example, if a third-party model is to be instantiated, the model can be used directly as it is. It is not necessary to contact the vendor and ask for API customization. It doesn't even have to be a C++ library. It can be C or Rust or D. Only C++ header describing the library interface is necessary. Okay, now all necessary libraries have been loaded. In the next step, we use some convenience functionality from the SCC library to configure the VP simulation. We set lock level in C++ to the same level as in Python. We configure SCC to enable trace, which means VP simulation will write SCV and VCD traces. In the next step, we could instantiate our DUT, but we have to create it first. Okay, let's create a structural top level of the system in a separate Python module. Here we have to import again cppyy and PySysC. This time we'll also need connection, signal and clock. Then we create a Python class for the structural top level module. We write an init function and all design components will be instantiated and wired here. Now we can instantiate components of the system. Let's start with the reset generator. PySysC module create function is kind of a factory. It takes the class to be instantiated and the instance name and returns an object of a class. In this particular case, it is the RSTGen class in TJFS VP namespace. Now we will instantiate a router as an example of a template class. The template parameter is specified in the square brackets. We instantiate router here with a bus width of 32. So as you see here, we can easily use C++ templates in Python. All other modules are instantiated in the same manner. Okay, all modules are instantiated and now we can start to connect them. PySysC provides a clock generator class, which is based on scClock. We create a clock instance here with a clock period of 64.5 nanoseconds and connect this clock to EON interrupt module and to the core. In the next step, we apply a normal signal and wire it immediately from source to sink. What is remarkable here is that no signal type is specified. This is not necessary because the signal class checks the type of the source and the target and creates an according ST signal. This is the Pythonization layer of PySysC. The type information is no longer necessary and also syntax is closer to Python than to C++ at this point. In PySysC, the type information is basically hidden from the user in Python classes. We create kind of a chain here and wire reset to multiple targets within a single command. By the way, we can also wire multiple signals with list comprehension, so one inline for loop. And in the same way, we could instantiate several modules in inline. Now to the sockets. The connection class does for the sockets exactly the same what the signal class does for signals. Here we connect the core initiator socket to the router target socket. Let me just copy paste the rest of the routing wiring. Okay, now everything is connected. The top level hierarchy is now ready and can be instantiated. We import top module from TGC top and create an instance of it. Finally, we have to load a test firmware to prove that the system is actually working. Interesting is here that to load the firmware we used this elf file property of the ISS core. Basically, elf file is a CCI property. So as you can see, we can configure CCI properties directly from Python. Now we can create a main section and start the simulation from there. The wiring is now complete, but it has not yet taken place until the call of the simulation run function. It was just noted that this wire should be connected to this port and this socket to that socket and so on, but all that can be changed until the simulation run function is called. Okay, now we can actually execute the VP simulation. The firmware is very simple. It basically calculates and prints the factorial of 10. First, we see the copyright from SystemC and then both Python and SystemC logging. And here we can see the result of this calculation. By the way, in PySysC, we can easily make use of the SystemC callbacks like end of elaboration, start of simulation, and so on. Let's print, for example, a message from the end of elaboration callback. And here we can see our message from the callback function. Okay, we just created a working VP system top level in Python. In the simulation directory, we will find a VCD and a CV traces. Takes log file is a SystemC verification library transaction recording trace. These trace files can be visualized and analyzed with different tools, for example with Impulse, and for that I am handing over to Thomas Haber.